All right, Algebra 2, Section 5.3, Graphing Radical Functions. Okay, this is going to be a little bit of a flashback to all of our different sections on graphing because we're going to go back into our transformations again. But first we need to talk about some new parent functions. Okay, so we're going to be graphing radical functions, writing those transformations of radical functions. And then we're going to be graphing parabolas and circles. I know we spent a lot of time on parabolas, but we're going to look at how to graph them using our technology, using our graphing calculator. And same with circles. How do we graph those things? Okay, and you'll see where radical functions will fit into those. Okay, so first a radical function. Okay, a radical function, what is a radical function? Well, first of all, it's a function that contains a radical expression. So it has a radical expression. Okay. Again, what we mean by radical again is that radical sign there with some index in here. A radical expression with the independent variable, that's our x, our independent variable in the radicand. Meaning my independent or my x is inside of that radical. For example, the fourth root of x. Okay, that is a radical function. Now, if I had the cube root of 3 times x, this function equals f of x equals the cube root of 3 times x. This is not a radical function, because my x isn't inside the square root. This is linear. Okay, this would be the square root with a slope of the square root of 3. Well, it's not pretty linear, but this one's not a radical function. Your x, your independent variable, has to be inside that radicand. Okay, so if we look at our general square root function, so our most basic radical function is our square root, or whatever we put in, we take the square root of that. So when we put in a 0, the square root of 0 is 0, the square root of 1 is 1, the square root of 2 is the square root of 4 is 2. The square root of 9 is 3. Okay. So there's our general square root function. And if we think of this as a function, we can think of it as its domain and range. Okay. And it's increasing, decreasing, maximum, minimum. Okay. Our general parent function of the square root is increasing. You see it's always going up. As I put bigger and bigger and bigger numbers in, the square root of that is going to be bigger and bigger and bigger numbers. Okay, my domain is interesting here because you can't take the square root. We know we can't take the square root of a negative and get a real number. So to keep this in our real number, the only x's I can put in it are positive x's. So our mathematical way of saying positive x's, our x's have to be greater than or equal to 0. But since I'm only putting positive x's in, that means for my range, I'm only going to be getting positive y's out. So my y's are also going to be greater than or equal to 0. Okay, for the general parent. Now if I shift this up or down or left or right, that's going to change these domain and ranges. So keep that in mind. Like if this was shifted over to the left, that's going to change my domain because I can put negatives into it then. Okay, so kind of be keeping that in mind. Okay, our cube root function. Our cube root function is kind of interesting in that we can put negatives into that because I can take the cube root of a negative 8. It would give me a negative 2. Okay, and it kind of, it doesn't go up as fast because I need to put really, really big numbers in to get really, really big numbers out. Okay, so the domain here of our cube root function, my x is all real numbers. All real numbers are fancy R, and our range is also all real numbers because we can get any number out of the sky as well. So your domain and range for a cube root, because since we can take the cube root of a negative, it's okay. We can put negatives in, so that means we can get negatives out. Okay. So here let's graph these functions, identify the domain and range of each function. I'm going to graph these by creating a table of values. My x's and y's, or my x's, my f of x's, when I put a 0 in. So I always start with a 0. The square root of 1/4 times 0. 1/4 times 0 is 0. Square root of 0 is 0. So we'd have the point 0, 0. Okay. And then if you're not sure on your other ones, we can go ahead and take the square root of 1/4, I don't know, we want to do times 1, is 1/2. Okay, so you'd have the point 1, 1/2. Okay, now what about 2? So I'm just going to go up and grab that, hit 2. 2 is 0.7. So we have 2.7. Okay, so what about 3? You can also second enter. It brings back your previous answer. 3, we get 0.8. Second enter. Let's see if we can't get a nice number somewhere out of here. What about 4? 4 is 1. Okay, so 4 is 1. So it looks like it's going to kind of do a thing like this. And based on what we know about transformations, this 1/4 inside of here is going to be, since it's inside, it tells me it's going to be horizontal. Okay, oh, that's awful tiny. I can write that bigger. Since it's inside, we know it's going to be horizontal. And since it's 1/4 horizontal works backwards, it's going to be a horizontal stretch by 4. So basically I'm going to stretch all my points out this way 4. But now we have to ask ourselves, does that affect the domain? Well, it's a square root, so my domain's normally always positive. Is it still? Yeah, because it still starts here for my x's at 0. Because again, for domain, we're looking at the x values there. So my domain is still x has to be greater than or equal to 0. What about my ranges? Well, my ranges are always going to be greater than or equal to 0. Why? Greater than or equal to 0. Again, domains are your x's, ranges are your y's. Domains are your x's, ranges are your y's. Some of us are still don't quite have that yet. Okay? So domain, what can you put in for x? And since this entire graph is going to be in quadrant 1, so really I don't need, oops, sorry, what's my arm? This entire graph is going to be in quadrant 1. Well, x's are positive in quadrant 1 and y's are positive in quadrant 1, which tells me that's my domain and range there. Okay. All right, next one. Here, again, I'm going to create a table of values. X, g of x. We have -3, the cube root of x. I'm going to think of that as -3 times x to the 1/3. It's the same as cube root. So I'm going to try some points when I put in a 0. Okay. When I put in a 0, we'll have -3 times 0 to the 1/3. That gives me 0. Okay. Now what about 1? So let's put a 1 in. When I put in a 1, we get a -3. Okay. What about a 2? 2, we get -3.78. 1, 2, 3. Okay. What about a 4? Just jumping around a bit. When we put in a 4, we get -4.76. So 1, 2, 3, 4, 1, 2, 3, 4.76, right about here. You can see it's kind of going to do a bit of a curve thing like that. Okay. Kind of like that a bit, maybe a little more down. Try a 5, other points like that to try to get an idea on what that's looking like. But since this is cube root, I can put negatives in it. What about a -1? Oh, sorry, I entered too soon. -1. We get -1, we get 3. Okay, so then I have a feeling, and if I put in a -2, I get positive 3.78. 3. Okay, so it's and then it's gonna go like that maybe. Kind of have that, and we can kind of see the curve up here, the parent function cube root. Okay, it's kind of gonna go like this because we know that this negative here is going to be a reflection. Okay, that negative out front is a reflection of the x-axis. Okay, so it's reflecting it in the x-axis, and you can see here it's going to flip this part down, flip that part up. Okay, and then the 3 out there is going to be a vertical stretch by 3. Okay. Okay, so how does that affect the domain? Well, if we're looking at my x's, this thing is going to be in quadrants 1 and 4 and in quadrants 2 and 3. So that tells me my domain is all real numbers, because it's going to be all the positive x's and all the negative x's. And then my range, it's going to go up for forever, which tells me that's a positive y. It's going to go down for forever here, negative y, so my range would also be all real numbers. Okay. All right, so now our transformations. We're going to go over transformations one more time. Okay, so I'm sure you're probably getting sick of these. Horizontal translations. Horizontal is left and right. Okay, again, those work backwards. So if my parent function's f of x, and they also work inside the function, so f of x plus 2 is going to move you to the left 2 units. F of x minus 2 is going to move you to the right 2 units. Okay. Hey, vertical translations, up or down, those work how we think they would. Horizontal, again, always work backwards. Vertical work how they think we would, and they're outside the function. So f of x plus 3, that's going to move it up 3 units. Now f of x minus 5, that's going to move it down 5 units. Okay, and again, make sure you notice here, this actually has it inside the function. Okay, so what that's going to look like in this case is if I had my new function, the square root of x plus 1, where the 1 is inside the square root there. That's going to move it to the left 1 unit. Whereas the difference down here, if I have the square root of x and then plus 1 out here on the outside, if it's out here on the outside, that's going to move it up 1. See the difference? Here it's inside on the x. Here it's outside that function. So inside's going to move it left or right. Outside's going to move it up or down. Okay. Our reflections. If we're going to reflect over the y-axis, that puts it in on the x, so that's going to be a y-axis reflection. So that's going to reflect it over this axis here. So it's going to flip it over, let's use a different color. It's going to take it, the points that are over here, it's going to flip over there, and flip over there. So it's just flipping back and forth across that y-axis. Okay, if I have the negative out front of the function, then that's going to be an x-axis reflection. And that's going to flip the stuff from above the x-axis to below and from below to above. Okay. Horizontal stretch. Remember, those ones work backwards. But those are inside on the function. Okay. So if f of a times x, okay, again, what we mean by backwards, okay, if a is greater than 1, it's going to be a shrink by 1 over a. If a is less than 1 but greater than 0, then that's going to be a stretch. Again, a stretch by 1 over a, the reciprocal of that. Again, that works backwards. And how this will look in my radical functions is h of x would be the square root of 2/3 x. It's inside there in my radical. So that would be a horizontal, in this case, horizontal stretch by 3/2, right? Reciprocal there. Okay. Vertical stretch happens out in front of the function. Okay, so if a is greater than 1, it's going to be a stretch by a. And if a is less than 1 but greater than 0, it's going to be a shrink by a. Okay. So how this will look if I had a 3 times the square root of x. Okay, it's multiplied there out front of the function. So here we want to describe the transformation. Okay, represented by g. So we want to look here. This first one is subtracting 3. That's inside the function. So that subtract 3 inside the function is going to shift this to the right 3 units. Okay, and then this plus 4 on the outside is then going to shift it up 4 units. Okay, so that plus 4 then is going to go up 4 units since it's outside there. Okay. On this next one here, we have a negative in here. So that negative sign is inside on the x here. That's negatives inside on the x there, so that's going to be a y-axis reflection. Okay, but then we have this 8. And that 8 is inside there as well. So since that 8's inside, it's going to be horizontal. And since horizontal works backwards, since that's an 8, it's bigger than 1, it's going to be a shrink. Horizontal shrink by 1/8. It's going to shrink it horizontally. It's going to squish it in like this. Okay. All right, example 3. The function e of d equals 0.25 times the square root of d. It approximates the number of seconds it takes a dropped object to fall d feet. So if I know how many feet it's fallen, it gives me how long that will take, okay, on Earth. The function m of d, 1.6 times e of d, approximates the number of seconds it takes a dropped object to fall d feet on Mars. Write a rule for m. Well, we know m of d equals 1.6 times e of d. But we know e of d equals this guy up here. So to write a rule for m of d, I would need to take 1.6 times e of d. And e of d is that guy right there. So times 0.25 square root of d. So 1.6 times 0.25 is 0.4 is my m of d. So there, we wrote our rule, m of d. How long does it take a dropped object to fall 64 feet on Mars? So 64 feet on Mars, that's the distance. So this is my d. We know d is 64 feet. We're trying to find the time. Okay, so that's my d. So we would have m of 64.4 times the square root of 64. The square of 64 is 8, so 0.4 times 8 is 3.2. So 3.2, and that would be the approximate number of seconds. It would take 3.2 seconds. All right. So next, example 4. And now we're writing rules again. So let the graph of G be a horizontal shrink by a factor of 1/6. So let's do this in pieces. We want a horizontal shrink by a factor of 1/6, followed by a translation 3 units to the left of this. So here's my parent right here. My parent is right here. So the first thing I want to do with it is a horizontal shrink by a factor of 1/6. So horizontal shrink by a factor of 1/6. So let's do that first. To do a horizontal shrink by a factor of 1/6, horizontal works backwards and it's inside the function. So I want to take f of 6x. It tells me I want to take this function, replace my x in here with a 6x. So I'd have the cube root of 6x. So there's my horizontal shrink by a factor of 6. Okay, followed by, next, I want a translation 3 units to the left. Again, that's horizontal, so that works backwards. So if I want to go 3 units to the left, I need to take x and add 6 inside the function. So I want to replace this x with an x plus 6. So I'd have the cube root of 6 times x plus 6 inside of there. So I'd have the cube root of 6 times x plus 6. Well, we can distribute that 6 into there to have my final answer. So my final rule for G would be the cube root of 6x plus 36. Okay, because I had to replace this x with an x plus 6. Again, do one step at a time. Okay, simplifying as you go. Okay, this last little bit is graphing parabolas and circles. What makes these interesting is these new parabolas. If you notice, this isn't a y equals. Your calculator can only graph things if they say y equals. So I have to get it to a y equals first. Okay, so I need to solve for y. So to do that, we have 1/2 y squared equals x. I'm going to get the y by itself by multiplying both sides by 2. Y squared equals 2x. And now then, I'm going to have to square root both sides. But be careful, when you square root both sides, you have plus or minus. Plus or minus the square root of 2x. So for me to get the entire graph of this, I'm going to have to graph both parts. I'm going to have to y equals the square root of 2x, y equals negative the square root of 2x. So I actually have to graph this in two different equations. The square root of 2x and negative the square root of 2x. I graph them, and I get this pretty, oh, sorry, my window's weird. Zoom 6 standard. And there I get my sideways parabola, and I can go ahead and trace it and get some points and plot some points here. So we have the point 0, 0, 1, 2, 2. So then with reflection, we'd also have this point 2, negative 2. It's the square root of 2x. 4.5, 3, 1, 2, 3, 4.5, 1, 2, 3. Okay, to get this bit of a parabola. Okay, all right, so we have to graph that in two pieces, two different equations. Okay, the same holds for, identify the vertex. The vertex here was 0, 0. Sorry, we didn't finish this problem. The vertex is at 0, 0. The direction, which way does it open? This one opens to the right. Okay, because it's opening to the right. Okay, use a graphing calculator to graph this. Again, we need to solve for y. So I'm going to subtract the x squared from both sides. So y squared equals 16 minus x squared. Again, now square root both sides. But by square rooting both sides, I have to do the plus or minus the square root of 16 minus x squared. So when I graph this on my calculator, the square root of 16 minus x squared, y equals negative the square root of 16 minus x squared. I have to graph this in two different parts. Oh, sorry. So we would graph the square root 16 minus x squared, and then negative the square root 16 minus x squared. Okay, so there's my circle. If you notice it looks more oval, that's because I'm not square. If you go to zoom 5 and square up, it looks much more circular. And for some reason, this is always a glitch with the TI-84s, is you notice it looks like there's an open gap here. There's really not. It's just, it's awful straight, and your calculator has a hard time graphing it. So we can trace here. It goes through point 0, 4, 1, 2, 3, 4. Okay, 1, 2, 3. Well, over here at 4 is 0. 1, 2, 3, 4, 0. Then 0, negative 4. Okay, so we have this little circle going right here. Eek. Sketch it the best you can in there. Identifying the radius. Okay, so where is the radius here? Well, the radius is distance from the center, which in this case is 0, 0 to one of the sides, so it would be 1, 2, 3, 4. The radius is 4. And identify the intercepts. If you notice, it's got 4 of them. 1, 2, 3, 4. So it has intercepts at the point 4, 0, negative 4, 0, and then 0, 4, 0, negative 4. It's all these points, 1, 2, 3, 4. Okay. All right, Desmos is actually an online graphing calculator that graphs these very beautifully. Okay, if you'd like some help with that, please let me know in class and I'll show you how to graph them using Desmos.